Okay, good afternoon. So today's class we will see how how we can just take through from signal processing to machine learning, and also where exactly these two may not be exactly, how these two can be slightly differentiated. So yesterday we stopped with this particular. Am I audible?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, I'll put it in presentation mode. PPT, is it very able to see?
Yes, ma'am.
Okay. So this was the example yesterday we were looking or we were discussing about this one. So in this particular example, when we look at this, so sensors, through different sensors, we are able to get the points, that is acquire the data, and to acquire, after acquiring the data, let me take the pen. So after acquiring the data, then we can, one thing is we can extract the features. Whenever I tell the features of that particular one, the features may be the important characteristics of that particular signal. So here the important characteristics of the signal means, when I tell important characteristics means, you can do some kind of time domain analysis. In time domain, you can extract some features, or you can take some kind of in Fourier domain also, that is in frequency domain also, or some features in time frequency domain also. So this is the kind of work which we can use in machine learning and deep learning, especially in machine learning, and also in some cases in deep learning model, as a pre-processing technique also. So here, from this acquired sensors, whatever the sensors data you are acquiring, after noise removal using some kind of filter, then we can extract some important features of this one. So here, whether or it can be about the peaks from the Fourier transform, or finding out the power spectral density of that one, or finding out some wavelet transform coefficients of this one. So here different coefficients are different values, you can extract it. So by observing the relationship between, suppose if you are you're getting two signals, maybe for this particular maybe running and walking of this one. So we can find out, or when you extract this one, maybe the value for this one may be different for this particular. So using some rule-based algorithm, we can just find out which features are differentiating these two, for these two actions, and based on that particular one, we can use that two features, maybe skewness and Fourier transform, or skewness and kurtosis of this particular one. Maybe these are the two features which is able to differentiate it. Then you can use these two features by observing from the observation, or from the some kind of correlations. Then you can write a simple rule-based algorithm, and you can find out. We can differentiate, or you can classify various activities. So the same example can be used maybe when you are finding out gesture recognition, or face recognition, or any of these simple cases of this particular one. Extracting the features, observe those features which are which features are able to differentiate it using some kind of correlation maps. Then use this rule-based one and use simple algorithms, and that one we can just take it, you can implement on any microcontroller or any DSP processor, or any FPGA processor. Okay, this is one kind of tell me. Yes, ma'am.
On that, you said we use statistics, kurtosis, and such parameters to define certain design rules.
Yes.
That will ensure feature extraction. But
yes.
Is that the only way we can do it, or are there other alternatives?
Other alternatives also are there.
Like for example, in case the statistical analysis cannot differentiate between two particular motions.
Correct.
Pretty well. Then what could we do in that case?
So in that particular case, Suppose that's what that is the way we moving forward to the next analysis. Maybe two features may not be sufficient. You may need features maybe in time domain. These are the time domain features. This is the frequency domain feature, or this may be time frequency domain features. So when you extract this whole of this particular one, approximately around 46 kinds of features may get it. Okay, so using rule based, when you write it, okay, if this feature, it is very difficult when you take it rule based kind of this one, because you have 46 features of this particular one, and to identify which features is different for that one, it is very difficult. It is some kind of ambiguity.
And we need to set priority also.
Correct. So especially these kind of cases where we are not able to distinguish with this one set of, with one person or with one activity, if we are not able to decide, then we can go for in a different way. The different way is we are using some kind of machine learning algorithm. So in that particular case, I am not depending only 1% data. What I am trying to get in this particular one is, because with 1% data, I could extract 46 features. With these 46 features, I have so much of confusion. This maybe we will get 0.4. I may get 0.36. This I may get something of. So it is very confusing, their data, and I am not able to decide whether this activity or this activity, or which two properties I have to take it to decide between two activities. In such cases, where accuracy comes into a picture, in this particular case, where I'm not able to decide this particular one, where in that, instead of collecting for one person or for one activity, or multiple people for this particular activities, I'll calculate it. Maybe 100 people or 1,000 people I can calculate it. So that means I have a set of data of 100 into, maybe I'm doing 5 activities, so 5 into 100, 500 data points and 46 features of this one. So now the matrix dimension, whole matrix dimension, it becomes 500 rows multiplied by 46.
46 columns,
so, 46 times. That means here the features are very much in this one. Now using this particular one manually to do it, or to analyze it physically, or to understand this one, it's very difficult. So for that particular one, we are going some kind of algorithm development. Some statistical algorithm kind of that particular one, which we are going to look at in course of that one. Maybe SVM, maybe KNN, K-means, so many kinds of classification algorithms are there. So using some kind of machine learning algorithms, we are going to give it to this particular one, so that this machine learning algorithm is, that means we are training one such model. So this model is going to tell that particular one, okay, for this particular, if this is the points of this particular one, this is the activity. It is going to tell that particular classification. Let us see afterwards what is that. So here, using this particular machine learning model, we are able to train the network. Once if you train the network, how our brain gets trained. So in the same way, we get train that particular model. Once the model is trained, so for any new person, when it enters, when you give some set of data from the sensors, and all the sensors, all the 46 features, whatever it is, if you give it, immediately it will tell whether it is this category or this category or this category or this. Any one category it can define. Okay, so here what I am trying to tell in this particular slide in this one is, it is signal processing. You can take this one as a pre-processing technique for a machine learning. Okay, or it can be, this is a part of that particular one. So where it is not possible to find the accuracy with one set of data, then you can collect the more set of data points of this one. Then you can go for a higher level of, to increase the accuracy of this one using this kind of a method. Okay, so here, but when it comes to implementation point of this one, there are two things which we look into. One is especially what is the hardware, or are you going to use it, and what is the application you are going to take it. There are some kind of applications where a battery power makes a sense of that one. That is, maybe if it is operating on a battery, it has to long last for so many days of that particular one. So in that case, what happens, the algorithm what you are going to design has to be a simple algorithm, and it has to take less number of iterations.
Lower number of operations, yeah.
Less number of iterations, and also
Ma'am, your voice is breaking.
it has to be in case of whatever
Ma'am, your
you
voice
are
is breaking.
telling, that complexity of that algorithm, or the
Ma'am, your voice is
maybe in
breaking.
case wherever it is possible. Hello?
Yes,
Yes,
hello,
ma'am.
ma'am.
Now we can hear you.
Okay. That time it was something. Okay, sorry. This particular one. Okay. Now let me just. So is this point clear? Is can just at least tell some of you whether this point is clear?
Yes, ma'am. What you told last is clear, ma'am.
Okay. So now let us move to the next kind of discussion. So in this particular one, when we look at this, so here when we just take it, it's a signal processing or machine learning or deep learning model. So in case of deep learning model, here we are not extracting features. Hello?
No,
Presentation is not.
presentation is not.
Now?
Yes, ma'am, we can see.
Yes, ma'am, it's visible now.
Ma'am, the previous slide, I don't think it's covered, ma'am, because we lost your audio there. Maybe the previous slide, I'm not sure.
Okay. Sujata, okay, I think now this is. Hello?
Yes, ma'am, we are able to hear you.
Okay. Keep it down. Okay, I think hope no more disturbances. So this is the one we were discussing that particular time. So these are the signals. Okay, this is where three types of things: signal processing, machine learning, and deep learning one. Okay, let us move to that. Now, yesterday's class we were just discussing it. Signal processing technique, whether it maybe smoothing operation or filtering operation or some kind of a classification also is possible. That one comes to some of the tasks, things may not be. Maybe a prediction also is possible to some extent, but to improve the accuracy and all the other things of this one, association or forecasting, estimation is possible both in signal processing as well as machine learning kind of. So to do some other extra task to improve the accuracy of this one, or to use the technology whatever is existing now, we will see why we have to go for that particular one, especially for association, clustering, grouping, and prediction analysis of this particular one. Maybe these machine learning and deep learning algorithms works better than signal processing algorithm. And when it comes to all these applications, especially when home assistant applications, the combination of signal processing, machine learning, and deep learning methods can be used. So this most of you are using, some of you are using these kind of home assistants. And also especially signal processing, this one works well with Wi-Fi. Here in this one, when you look at this one, different people are using routers, and here which it will identify which one has to be taken. So here the decision making of that particular one on how it has to be transmitted and all those things. And also when you are doing this whole of this process, when any online conference, when it is going on, there may be room reverberations. So how these room reverberations can be, or noise can be removed. So this is also a part of a signal processing one. So here in this one, when it comes to both signal processing and machine learning algorithms can be made use of. And especially with a large, as its autonomous driving vehicle is coming in a big way. So for analysis purpose and decision making of any of these vehicles, especially when you are going for autonomous vehicles, this is all the three are used in different ways: signal processing as well as machine learning and deep learning methods. So let us look at some more things. And when it comes to MRI also, so when you are taking MRI also, most of the, maybe till 10 to 15 years back, they were using the machine learning and signal processing algorithms. Now most of the things they're moving towards deep learning method. So here also, whatever the method I told you just now, so taking the MRI signals from different EEGs and analyzing this particular one, and here we can find out the Fourier transform of that one, some kind of Fourier transform is applied, and identifying some kind of anomalies also. So here to do this particular one, once again, to improve the accuracy, we can move towards deep learning and machine learning. So when you look at
yeah, ma'am. So like basically for deep learning, like we have to prepare an entire database of like different outcomes and stuff. Like normally, how long does it take to prepare this database or this network?
Data, how long it prepares?
Like how long does it take to like prepare the
data set?
Like basically for, yeah.
Okay, so here in this particular one, the amount of data it is requires when you look at, for just say in a normal signal processing algorithm, if you take it, it is very less data is efficient, but accuracy may not be that much good. But when you but accuracy will be good depending on the type of applications. Suppose there is an anomaly and you are able to identify with just Fourier transform or wavelet transform, it is sufficient. We need not go for machine learning. Whereas when it comes to machine learning, the data required is more compared to just signal processing, rule-based signal processing analysis. Whereas when you go for a deep learning network where we are not extracting the features, so there still more data is required. Maybe in tomorrow's class, I will give you the total AI, ML and DL and where all it is going to apply. Today's class, I will take only from DSP to ML. Okay, I will give you that particular one. Okay. So when you look at this, for all these things, especially from past 20 years, maybe advances in computers, as a lot of work is going on in GPUs and architecture, computer architecture, and because of this particular one, so computational complexity to put it onto a hardware, dedicated hardware, a lot of work has gone into that one. So it is dedicated architectures are available to implement it. High-speed algorithms, it's possible to implement it. Because of this particular one, so people have looked into alternatives, that is AI, ML and DL. This is one of the reasons of that. The second reason is that one, so here in this, as I just mentioned, feature extraction and analysis of this. So here there are various machine learning and deep learning models have come into picture. So this also has contributed to moving from basic signal processing algorithm to some kind of advanced machine learning and deep learning one. And also not only this particular one, the requirement what it is coming to picture is most of the things because of the IoT or autonomous car or home automation and all those things. A lot of work has gone into sensor technology and sensor integration. So because of this sensor technology and sensor integration, so here we have got a lot of data. They're able to acquire it to process or to use this for AI, ML and L. So these are the three main factors which influenced moving forward to this particular AI, ML and DL than the traditional case of signal processing one. But believe this, in all these things, signal processing is also existing, and it is a part of this particular one, and it can go without signal processing one. All these things we cannot go ahead of that. So signal processing also is there. Apart from signal processing, all these three things also come into picture. That's why in one of the recent papers it's mentioned the skill of this century. It's taken it as this ML or DL or whatever it is. This one, it is taken as a skill of this particular century also because of the advancement.
Excuse me, ma'am.
Yes, ma'am.
DL ML model in the sense it is just a embedded system, ma'am.
Yes, ma'am.
ML model in the sense it is just a computer program or the embedded system.
It is a computer program putting onto the embedded systems. So as I just mentioned in the previous long back in that particular one, any one of this, okay, let me take you that. So here when you take any system, when you develop it, so what you will do, so here we try to put it onto the first thing is we get the data or sensor data. Or after that we develop the algorithm. This is develop the algorithm. After developing the algorithm, then you put it onto a device. That is, you put it onto the either ARM controller or microprocessor, okay, microcontroller or an FPGA or any one or DSP processor, anything. Okay. And this particular one you can use dedicatedly. So this ARM processor, if you put it onto that one, then that chip you can use it in any one of the, maybe in your modems you can use it, or in your phone you can use it, or in any of the systems you can use it dedicatedly. Suppose if your algorithm and if this whole thing is a very complex one, that is a very big one, that is completely your sensor data and acquisition A to D converter and the total signal processing of this particular one. That means in this one you have used signal processing one as well as ML algorithms and DLL. Everything you have ported onto that one. Maybe using your programming or using Python script or using some kind of scripting language, you put it this particular. So here when you are doing it, there are two ways to do it. One is you can use these dedicated, these processors, available ARM processors, that is ARM Cortex or DSP, any of the DSP processor or any of the NVIDIA boards or any of the FPGA, existing FPGA boards of this one, or all those things you can port this algorithm onto the dedicated. So that is in your lab, whatever you have done it, porting the algorithm onto the hardware. There is one more method. This is one method. One more method is developing a ASIC chip itself. That means here your entire algorithm, you write it into blocks or some kind of maybe one arithmetic operation or multiplication operation or some kind of or some convolution operation. Like this you will write it in a block diagram level, you represent it. Then you write some kind of HDL code or Verilog code, and you go for the synthesis of this particular one, and then you make it layout, and then you go for ASIC design of this one. That means here this whole algorithm, whatever you are writing it, you are making it as a one chip, and that chip you can put it in place of either instead of this particular one, you can use it. So once the developing the algorithm is very important, that is one thing. After developing that one, based on whether you want to put it onto a dedicated hardware or you want to develop a chip, that depends on that one. So most of these autonomous car driving vehicles and all those things, to improve the speed of that one or to reduce the latency of that. So most of the things they may be working on ASIC design also. That is to work on this for whole algorithm to put it onto the, or here in this whatever the modem you are using it. So for the modems also inside that algorithm as ASIC chips they have been prepared. That's what most of the VLSI companies they may be working. So when they are working on to design the ASIC chip, there are two things. Maybe first algorithm, developing the algorithm, that is one group will do, and writing this HDL code design of this particular one, layout design of this one, then verification of that one, then fabrication of that one, after fabrication, testing of this particular one, which in your VLSA class, the whole flow that it is. So when you take any of this, any module, when you take your modem itself, in this modem itself, so all the whatever I just mentioned, all these things goes into picture. It is algorithm development and also chip development. So both are equally is required to develop any one of this, any of these modules. Is it okay? Shall I go ahead?
Ma'am, but you said that there will be a lot of models and a lot of models have come up. So to use for another purpose, that means the program should be changed now, the algorithm must be changed.
Yes, in which one? In which?
In any of them.
Yes, we have to change the algorithm. That's why engineers say.
To compute the data will change now, ma'am. That means there will be a lot of storage which already stores the data for one application. So one model can be used for many applications, ma'am.
One model is not used for many applications. Here in this particular one, whatever model you are developing, it is dedicated for that particular application. Suppose when you are taking this modem, only that modem, whatever they have developed, that particular one, it is only useful for that. Suppose in your home automation. So home automation, there are different modules are there. In that particular one is maybe whatever you are talking, it has to identify, that is speech recognition, and that particular one has to be transmitted to that one. That means that it has to be controlled. So there are different sub-modules of this one. In this one, suppose this sub-module may be useful only for this. So here in this, whatever the application is there, it is dependent or it is application based. It is not a general model where you can use it for entire set of or for other applications. Whatever you are using for autonomous driver, you cannot use it for this particular one, or you cannot use for gesture recognition.
Done.
Okay, so that's why there are various models and in that particular one also, when you are developing the model, as I just mentioned, what are the things we have to keep it in mind? All the things we have to keep it in mind. So what is the complexity of the algorithm? How we can reduce the algorithm? Or what is the memory capacity of this particular one? Where you want to put it? What is the battery life of that particular one? How much time it can take of that particular? Or in this one, how it's compatible with the other device? Or this one small module, once if a sub-module, when you use it, whether this sub-module, can I use it for something else? Okay. So in this way, we will, that is the reason many people will be working on that particular one parallelly and going to freeze out the design part itself. So after designing this one, then we can go for the simulation part of it. Is it okay? We will take one case study. Anyway, maybe after 1 or 2 classes, we'll take one case study. Shall I go ahead?
Yes, ma'am. Yes, ma'am.
Okay. So here, when at this point of time, hope I'm able to convince you that signal processing to machine. So signal processing, it is for analysis purpose. We can take it. Okay. And also some kind of filtering operations we can take it, and whereas in this particular one, where power consumption plays a very important role, or whenever they are putting onto a hardware device, or in that particular one, we can look this kind of thing. And to improve the accuracy of this one, or to reduce the latency of that one, something of kind of this, we can look for different kinds of ML algorithms also. So let me give you conceptually how we can derive from this DSP to or towards the ML and DL. So in this half an hour, another, what do you have next, sir?
CS1.
CS1. Okay, and the 20 minutes I have. So I need not tell about the signals systems already we have seen, and 1D signal, 2D signal, and different types of continuous signals and systems of this one. So here in this, when you see the systems of this, there are in this signals itself we have seen deterministic signal and random signal. And here the most of the data what you are getting here from the sensors or from the devices or from any transducers, whatever the data you are getting is random data. So from this random data to process that one or to analyze that one, so here we have to see whether the data is stationary data or non-stationary data. So here I'll not go in depth of that one because I want to cover something else. So based on this, whether it is a deterministic signal or a random signal, and from this particular one we'll find out what type of filter we want to use it and what type of processing system we want to use it or what type of model we want to develop it. That's the one we are going to see. So when it comes to a probabilistic model, all these speech processing signal or music signal or radar signal, sonar signal, all these signals are random in nature. So that's why to make it deterministic, some kind of give that one, we go for especially find out the statistical characteristics of that one. So by finding out the statistical characteristics of that one, some kind of randomness we are able to remove it and bring it to a deterministic in nature of this one. So this the systems in this one. So here previous classes you have studied about different properties of the systems, linearity, time invariant, memory, and all those things. And out of all the system properties, two important properties we have taken it. One is the linearity property and time invariant property. So from this linearity and time invariant property, we very well we understood that one. If input is a deterministic signal, system is an LTI system, the output is nothing but a linear convolution of this. So here this is the linear convolution of this one. So here also not much time we need not spend on that one. So here when it is a linear convolution system of this, so here any system, if it is a linear LTI system, if input is a deterministic kind of signals of this one, and this operation, whatever is going to do it, that operation in signal processing is a filtering operation. So as I just mentioned, this is one kind of filtering, need not be stick on to that one kind of filtering operation of this one. So here in this kind of filtering operation, so here we are going to study in signal processing the filtering operation to remove unwanted signals of this one, and also when you are removing unwanted frequencies or unwanted the parts of the signal, that means it's not going to add any new frequencies to the signals. So let us little more move into that one. So here when you look at that one, there are already analog filters and digital filters comes into picture. Analog filters means input is analog signal and filter also is using analog passive components, RC, LC and all those things. Whereas digital filters is input is digital signal and filter components are discrete component. Discrete components means adder, subadder, multiplier and a shifter. So using this particular one, you are going to do it. So this also not. So now when you look at this one historically, most of the till 1960s, we can tell that one, most of the filters or all the filters are of using analog components. That is using resistors, capacitors, inductors. Maybe in 1960, after the invention of the computers, and most of the digital signal process have come into picture. So after this particular one, so all these, whatever the models are there or whatever the applications are there or whatever the systems are there, move from analog domain to a digital domain. So here in this digital domain, when I tell digital domain, it is not just the DSP processor. It can be a DSP processor, or it can be gate arrays, that is FPGAs, or it can be a microcontroller. So here when I tell DSP or digital processor or digital filter or anything, so the digital processors are whatever we are studying in various courses, maybe a VLSA course, or it may be microcontroller, ARM controller, and all those things are embedded system, or any DSP, general purpose DSP processors. So I'll move to this particular one. I will not take the advantages and disadvantages of this particular one. Let me move to. So here in this one, when when any DSP algorithm, when you take it, as I just mentioned, we'll find out the characteristics of that one. So what are the characteristics? Maybe it's in the time domain characteristics and the frequency domain characteristics. So whenever you are analyzing the signal in DSP algorithm, time domain characteristics means it is h of n or h of n in difference equation, and in frequency domain is whether it is in the Fourier domain or in the Z domain. So based on this whole of the discussion for the signal processing, when it comes, the filters can be frequency selective filters like IAR, FIR kind of filters, or adaptive filters, or Wiener filters, optimum filters, or Kalman filters, or wavelet filters. How these filters differentiated? So when you look at this particular small diagram, whatever I have given it, so here in this case, so here the system can be, it can be a time invariant system, or it can be a time varying system, or input can be a deterministic signal, or input can be a random signal, or noise can be a Gaussian noise or non-Gaussian noise. Okay, so anyway, all these things I will be teaching, but as an introduction, let us see. So based on these combinations of this one, whether the system is a time invariant system, or whether system is a time varying system, or whether input is a deterministic signal, or input is a random signal, or input noise, whatever the noise added is a Gaussian noise or a non-Gaussian noise, or whether it is a non-linear system. So based on these combinations of this particular one, these filters are classified. So here this IAR and FIR filter which you are going to study in this particular semester is when input is maybe deterministic signal or system is an LTI system. Whereas adaptive filter is when in this particular case input is a random signal and system is a time varying system of this particular. So here in this case, in this revision filters, we have seen whether it is a low pass filter or high pass filter or band pass or band elimination filter. And based on the band pass and band elimination filters of this, we have seen the difference equation. This is the one which, so whenever you take the system, so which defines output to input, so system X of n and Y of n and H of n is a system response. In that particular one, these things Y of n and X of n are related by using linear difference equation. So in this linear difference equation, when you look at linear difference equation, output depends on three parameters: past output and the present output and the present input. So present input, past input and the past output of it. So here based on this particular one, when you draw the H of Z, so you will get poles and zero structure. This is some kind of transfer function. So as I just mentioned, whenever you are modeling any system, that means as I just mentioned, maybe reverberations, room reverberations, or maybe vocal cord, or maybe unknown earth model. You tell anything of this particular one. So any noise model, any communication channel. So whenever you use a word model, model is nothing but some kind of transfer function. So some kind of transfer function means it is poles and zeros of this particular. So whenever this comes poles and zeros of this one, always we can represent that one as in the form of a filter. So as I just mentioned the previous speech processing one, whether your vocal cord or your lungs one or your nose, whatever the particular one, each one acts as a filter. Each one can be represented, each one can be modeled. Each one can be modeled means each one can be represented in the form of maybe H of Z is equal to 1 plus A Z inverse plus B Z to the power of minus 2 divided by 2 plus something. Some kind of pole zero model we can represent. So from this pole zero model may be different for your vocal cord, it may be different for, that means these parameters may be different for you, these parameters may be different for me, or it may be different from maybe for Muhammad Rafi and all those things of this particular. So that model of, that is the one which decides what is that particular model. So in signal processing, that is also possible. So from this basic model of the whatever we have seen, from this basic model we can define whether the filter is IAR filter or FIR filter. So if this model depends on both the things, then that filter is IAR filter in this particular case. If it depends only on output of this one, then that particular one is FIR. So here this FIR model I'll take into consideration. Next under 10 minutes I'll take you through the next discussion. So when you look at the
IR and FIR, like the differences.
Differences you don't worry. Differences anyway. When it comes to the class, I will tell you. Okay. So the differences in this particular one, what you have to understand, the difference is only in this. So here, in case of IAR model, it depends on both on the past input, present input, past input, and the past output. So it is a pole zero model. That means both numerator and denominator it is there. So like this kind of this one. So entirely it depends, and it is a kind of the. Whereas when it comes to IAR filter, FIR filter, which is required for the further discussion, that's why I want to concentrate more on this. So when it comes to FIR discussion, so in this FIR discussion, it depends only on the past input, present input and the past input. That is, there is no past output. Let me show you. That means in this equation, in this linear difference equation, this y of n depends only on this particular parameter, not on this parameter. So as depends only on this particular parameter, so here let us see that one, because this is the one which is required for further discussion. That's why I want to concentrate. So here, so this particular one is the one which output depends on only on the input and the past inputs. So when you write this kind of expression, the same thing if you represent in kind of a block diagram representation, x of n is the input. So x of n minus 1 pass through one z inverse term, x of n minus 1, x of n minus 2, x of n, and multiplied by different weights, different h of 0, h of 1. So the same expression when it's implemented, you are getting this kind of. So this is an FIR filter structure, where in this FIR filter structures, we previously predefined these values from h of 0 to h of n. That means, let me tell you one more point at this one. Suppose there is a signal. This particular one, some kind of noise is added. Maybe the noise may be some 60 hertz noise is added to this one. That way z kind of sound it is coming there. Now we want to remove that particular one. So this one we are passing through a filter, and this signal may be from 300 hertz to 3 kilohertz signal. 300 hertz to 3 kilohertz signal, but noise is added to that one. So what we will do in this particular case, so we will design a high pass filter where 60 hertz of noise we want to remove it, and we, after getting this particular one, we get a signal where noise is removed. So here in this one, when you look at this, I know what is the frequency I want to remove. That's why it's a frequency selective filter. So when I know what is the frequency when I want to remove it, so in that particular case, I design a filter, that is all these filter coefficients using some method, so that these particular 60 hertz can be removed. That means, so here I know what is the input, what is the frequency I want to remove it. So accordingly, I design that particular one, and accordingly, I fix these coefficients. Okay, till here you just remember this one. So these weights, whatever I have given, are the predefined weights of this one. So using this concept little more, I will take you to the next one. So here this FIR filter, whatever I am using it, I am designed here is, it's the predefined coefficients of this one. Next, let me take you to that one. There is a case where it is not possible. So in this particular one, when you look at this particular figure, here one is piano one is some kind of two instruments, one singer's voice, and there is, when you add all these things, AX1 of T, AX2 of T and all that, and there is a background noise also. Now we want to remove this background noise. Accordingly, when you look at this particular one, what happens? So you have to make A1 to 0. Then only this background, this whole term will go. Then only it is possible. But if you remove A1 to, if you make A1 to 0, what happens? This singing, that voice itself will not be there. So there should be an alternate way to reduce this particular term. So what is that alternate way to reduce this particular term? So the alternate way to reduce this particular term is, when you look at in the transform domain, I could, when I analyze it, when you plot the Fourier transform of that one, I could,
function of G omega.
What I could make out is, this noise term is not overlapping with the regular signal of this one. There is somewhere it is in that. Or in this, if it is a separable one, I can use some kind of, this kind of filter, whatever it is there. Suppose there is some cases where it is within this particular signal itself. So if within this particular signal, if it is there, then it is not possible to design it. That means within this particular signal itself means, so if there is a noise term in this, if suppose the noise term itself is here, somewhere here. So what happens if you try to remove this one using this? So the signal also will go. That is, when the signal and the noise, if there is any overlap, then in that particular case, the previous method, whatever I told, it is not possible to use it. In such cases, we have to go for adaptive filter system. Can I take another 2 minutes?
Yes, ma'am.
Okay, just you give me 2 minutes of time only, because I don't want to leave at this point. So here in this case of adaptive filter kind of this one, same concept of adaptive, if you remember this one, same FIR filter only used it, but here in this one, these weights are not fixed weights. Why it is not fixed weights? Because I don't know what is the signal I want to remove it. Because according to the previous discussion, I cannot, if the signal is at this particular point, if the noise is at this point, I cannot use a previous kind of discussion or previous kind of filter. Because if I remove this one, signal also will go. So that is the reason what I'm trying to do is, we're going for an adaptive system kind of. So in this adaptive system kind of this particular one, when you look at, so here what the kind of this one I'm going to give it. Here I will give signal plus noise. Here we'll give noise signal, and here in this adaptive filter, these weights are adjusted in such a way that this iteration process goes in such a way that this noise is equivalent to this noise. That means this adaptive filter is optimized when these two noises are equal. So till then, these weights are adjusted. So how it is adjusted is using some kind of learning algorithms. So here, this is the learning algorithm, which some of the algorithms which you're going to study in machine learnings of this particular one. So using some of the learning algorithms, what this algorithm does is, it updates the weights in such a way that at the whatever the noise or whatever the error you are getting at this particular point is minimized. So here from why we are going for this particular one, because in the previous one we have seen that there is an overlap of noise and signal spectrum. Because there is an overlap of noise and signal spectrum, because of that particular one, instead of defining predefined calculations, we are some iterative method or some adaptive method, We are trying to adjust the weights of this particular one. That is H0, H1, H2, H3. Here we call it as W0, W1. So adjust the weights in such a way that this particular one at the end of system, the error is minimized. So this is the basic model for your neural network or your deep learning network or your machine learning algorithm. So this particular one, next class we will see. I'll try to connect you with the how it is biological neural networks and how the processing of the learning algorithms it happens. Okay.
Can I ask a doubt here?
Yes.
If you go back to adaptive filters, the slide. Yeah, here there is a primary input which you said is just the noise component. How are we going to model the noise component itself in the first place?
Okay, in this particular one, we are going to model the noises. Once again, maybe based on our this particular one, what type of noise you're going to suppose. Maybe Gaussian noise, or it may be some kind of random noise of this one, or sometimes. So here in this particular one with a predefined we'll have some knowledge what type of noise we want to give at this particular point.
Ma'am, if we already have an estimate of what sort of noise is available, for example, like you said, Gaussian, then why do we need ML? We could just subtract the noise that we want to eliminate, let's say Gaussian, from the previous example, the audio example. And you would get the desired response. Like
here, I'm not using ML. Here, I'm not using ML. Okay. Here, this is some kind of model. In this one, here becomes some kind of learning algorithms. These learning algorithms we may take as a kind of ML. So still, I have not come to ML part. Okay. This whole thing is not ML. This whole thing is not ML.
Ma'am, still, whatever response you get will not be correct.
Here.
So what we're doing here is we have a primary input, which is the noise model.
Correct.
That we want to remove from the audio. And the audio is a reference input. The audio, like for example, a concert. The output of the adaptive filter is an estimate of the noise based on the coefficients that are adjusted.
Correct.
So that is going to a subtractor.
Correct.
And the output must be minimized.
Correct. So here when I tell this particular one, this whole process is a random process system. So when whole process is a random process system, here what I am going to tell is take it as a mean square error. You may get doubt. Here S plus N is there, here N is there. So N cap, actually it is one is N1, other one is N2. So here it will not be.
Understood, ma'am. That's understood, but you will get an output which is 0, but you have to have a good noise model for that first.
So here in this particular one, what happens is now most of your mobiles has this particular kind. So how it is? Suppose you are standing in a railway station. Okay. So what happens is first few milliseconds or first some kind of microseconds of that particular one, whatever the noise is there, that is the desired noise of that one, that has to get subtracted from the signal it is coming. So in the beginning, that model gets trained in such a way that whatever this adaptive filter one, whatever it is there, it gets trained in such a way that this noise, an output of the noise, whatever it is you are getting, and the noise is modeled here in this one, it gets subtracted. So
you're saying we keep iterating the noise.
This is correct. For few milliseconds or microseconds of that one, this training, it gets trained. This is a training phase. Once if it is trained, this adaptive filter, these coefficients, it becomes constant.
Yeah, but that's what I'm saying, ma'am. The training will only be as good as the noise model, the primary input.
Yes, sir.
So if it like you cannot model any particular noise model because noise is very random.
So here that's why here we are not modeling. It is these coefficients are adjusted in such a way that
those coefficients are adjusted per the assumption that your noise model is perfectly correct.
Here we need not have a noise model. Here we are not at all modeling anything. In this whole system, we are not modeling anything.
Ma'am, so
Okay.
how are you applying the primary input?
Here we are not modeling anything. Directly input is coming. Maybe you just take traffic noise. Directly signal is coming. Okay. Maybe first 30 samples or first 128 samples or some samples we will be taking. So
Ma'am,
that particular.
So you're taking the noise. So you're taking the
correct.
noise from a traffic model and
It's
subtracting
not
that
a model.
from.
We are not modeling. What you have to understand at this particular point is we are not modeling anything. Without modeling of this particular one, directly there are different algorithms which can take that one. So here we are not modeling any of the noise. There is no modeling concepts in adaptive system.
So how are you supplying primary input?
Okay, so supplying primary input is now here when you switch on this particular one, or when you go to railway station, whatever the input you are getting, that itself is a noise.
Okay,
that it's so what happens is before your speech signal comes, something is already coming into picture when you just go outside immediately. So something is already receiving it. So when something is already receiving means some input is there to your sensor.
Yeah, but that noise will be random. That noise can change with trend.
Correct. So that's why this adaptive system, the input is a random signal. It is not a deterministic signal. The input for this adaptive system or adaptive filter, this one we call it as an adaptive filter. So the input to this random system or adaptive system input is a random signal. And also here the adaptive filter, this is a time varying system. That means it keep time varying with respect to time. So in the beginning, whatever the model I told you, there are 3 models or 4 models. Okay.
But then it is important that it converges very quickly.
That depends on what is the conversion rate, that is eta convergence parameter you are going to take it. What is the algorithm you are going to use it? How many samples you are going to take it? What is the gradient algorithm you are going to use it? What is the steepest gradient of that particular one you are going to use it? So it goes with the different kinds of this particular one. That is also equally important.
Are there examples of this, like industry examples?
Yes. Actually, in all the noise cancel, that is now you just take your as I just mentioned, headphones you take it. You have headphones or this whatever the phones or whatever we are using it. All those things from 100 rupees to 1 lakh it is there. Correct? So that means 100 rupees one, if you put it, it's so much of noise, both the sides it is there. Whereas when you put it 1 lakh one, definitely fan noise also you cannot listen to that one. That means there is an echo canceller in that particular one. In all your modems, all your phones, all your here when I am talking in this particular room, whatever I am talking in this particular room, it reverberates in that particular one and it comes back and it goes. So there is a noise canceller in that particular. In your Google Meet, whatever you are using it, if you just go to one of the settings, there are some kind of noise models which you can select it also. Okay, so for all those, ask me.
I want to clarify my understanding. Could you go back to that slide?
Which one?
Of the adaptive filters.
Which one?
Adaptive filters.
Adaptive filters, I will, you give me, maybe after completing some time, I will take on adaptive filter class only. It's not there in the syllabus. It's not there in the syllabus. I can teach you.
It's interesting, ma'am.
It's very interesting. It's very, actually there are different, this is one model I have given. There are 4 models are there. That is, as I just mentioned, 4 models applications itself. That's the reason I asked you which afternoons we are free, all 4 batches, so that I can teach some kinds of adaptive systems, one VLSI in signal processing and embedded into signal processing, and also multi-rate signal processing. All those things I want to teach. That is the reason I asked you which afternoons you are free.
Ma'am, so my question was over here, if we take primary input and reference input as the same thing, and
it's not same thing. It is not same thing.
It is not the same thing.
It's not the same. Now you just imagine. Oh, I'll tell you.
Okay.
Now there are base stations, geo and so many these antennas there. So this particular one, we have to find out which side are where the signal strength is more. Okay, so to find out where the signal strength is more, so from the different antennas you may be receiving different signals. Maybe in some places you will get the strength of the signal may be more, some places strength of the signal may be less. So in that particular one, maybe you may be coming to the correctly within that beam width or within that particular region of conversion or region of beam of that particular one. So here in this case also, so to get maximum beam of this one, there are some kind of side lobes comes into picture. So how well you reduce that particular side lobes? So that way it is. Tell me, ask me.
So like the reference input is constant. Primary input is what we are getting from the environment.
Others can attend other classes because, tell me.
And we set some values for the like adaptive filter, like the initial value.
One more example I'll give you. Just wait. One more example is, suppose.
Can you give a real world example? With
all these are real world examples.
Like for example, like you give the example of the railway station.
I'll give you.
Can you explain how I'm providing inputs to both primary and reference?
Wait, I'll give you. So here in this one, suppose ECG of a baby if you are taking. Okay. So this is ECG of a baby. So when you are taking ECG of a baby, that is fetal mother inside. So when you are taking ECG of that one, with that particular one, other things also comes into picture. What are the other things? Maybe because fetal ECG is very feeble. So in that one, a mother's one, also some kind of thermal noise, fan noise, and all those things. So here we will take that particular one as signal plus noise of this one. Okay. And this particular one, but at the end of that one, only that baby's ECG is required. This is the required signal. Correct? So in this particular case, what we will do it here in this as a primary one, we don't know what all the other components. All the other components we will take it as a noise component. So when you take all other things are noise component, so here in this particular signal of this particular one. So here when I take the other components as noise signal, noise can be, you can use a rand function of this particular one, or you can take, you can model Gaussian noise of this one, or what generally it is done in this particular one is, we'll find out what is the model of this one. That means we'll collect all these signals and we'll find out the PST of that particular one and what is that noise it consists of. What is the approximate function of that one? Whether it is approximating to Gaussian one, or whether it is approximating to Laplacian, or whether it is approximating to randomness of this particular one. Because why we take random noise or Gaussian noise is because this one contains all types of frequencies. All types of frequencies minus infinity frequency to plus, that is infinite frequency component. These infinite frequency components in frequency domain, when you are trying to represent, last class in signals and systems I have mentioned, this is the frequency spectrum. So that is constant frequency spectrum. But when you are taking a band limited kind of this one, because I don't have from here to here. So when you are taking a band limited kind of this one, so the limit of this particular one, it is approximated to a Gaussian distribution of this one. So here, this approximately when you take Gaussian distribution of this particular kind of system, so noise of this. So this noise, when you take H of n, this is the distribution. When you take H of n, you will get some kind of signals, some kind of noise signal. That means 0.001, 0.00, something of that particular values you get. So what happens each time? You just imagine this is stored in a register. Okay, DMA controller and all those interrupt based you have studied. No? So imagine all these are stored in kind of register. Maybe I'm using a register of 1024. So 1024 samples are pushed, and here I am getting 1024 samples, or one sample only 1000. These 1024 samples I am passing through this particular one. Here also the same signal plus noise I used as a batch processing of block of 1024. We have studied block convolution. So 1024 and 1024. So here when you, these 1024 points, I'm passing it. So here I'm using maybe a filter 1024 a tap filter. So when I'm trapping, so you are getting one more register passed to this one. Some kind of convolution operation is happened because anything when it is passed to that one, some convolution